So, in this module, in the first lecture, we learnt about the phase plane and the harmonic oscillator. We saw the description of the phase plane and how it can give a portrait of the harmonic oscillator problem. Then in the second lecture, we saw the critical points, we saw the meaning of critical points, we looked at the problem of the pendulum and did linear stability analysis to get a phase portrait of the pendulum. In lecture 3, we saw the classification of critical points, okay, using the linearized system. In lecture 4, we saw population dynamics, where we analyzed the Lotka-Volterra model. Okay. So let us do a few practice problems. Okay. The first problem that I want to do is involves the harmonic oscillator, and I have asked you to draw the phase plane of this harmonic oscillator. So, consider a damped harmonic oscillator given by this equation, x double dot plus phi x dot plus 4 x equal to 0. Identify the critical points and classify them. Draw the phase plane picture. If x 0 equal to 1 and x dot of 0 equal to 0, solve and depict in phase plane. So at t equal to 0, if you had this, okay, and this equal to 0, solve and depict in the phase plane. So the strategy to solve this is to write this as a system of first order ODEs, set each derivatives to 0, and you solve for the critical points, eigenvalues, and so on. Okay. So let us look at the solution. So first we'll write it as a system x dot equal to y and y dot equal to minus phi y minus 4 x. So clearly the critical point is x equal to y equal to 0, because if you set x dot equal to 0, you will get y equal to 0, and if you put y equal to 0 in this and you set y dot equal to 0, then x has to be 0. So x equal to y equal to 0 is the only critical point of this system. Since it is a linear system, this can only be the critical point. Okay. So this is not a nonlinear system, this is a linear system. Okay. So we can go ahead, we can write the matrix 0 1 minus 4 minus 5. We solve for the eigenvalues of this matrix, and you get the eigenvalues by this simple quadratic equation. You will get eigenvalues of minus 4 or minus 1. Now both the eigenvalues are real and both are negative, okay, and they are not equal to each other. So both are real, both are negative, or are not equal to each other. So that is an asymptotically stable critical point, and in fact it is a node. And so if you take lambda equal to minus 4, then your eigenvector is 1 minus 4, lambda equal to minus 1, your eigenvector is 1 minus 1. So basically if you look at the solutions, okay, this is the more slowly, this is a smaller eigenvalue, and that is going to dominate the behavior at long times. I should do this again. So the long time so let's just go ahead and draw the phase space picture. So you have lambda equal to y equal to minus x and y equal to minus 4 x, and what we said is that this will have a term that looks like e to the minus t. This will have a term that looks like e to the minus 4 t. So clearly this let's do this again, 4 x and y equal to minus x. Okay. So clearly it is the y equal to minus x that is going to dominate the behavior at long times. So what the solutions will look like. So suppose you start from somewhere, then eventually you will go to 0 along this, asymptotically you will go along y equal to minus x. So asymptotically you will approach along y equal to minus x, and you would so your solutions would look something like this. Okay. If you are in this part, okay, where x is greater than 0. So if x is greater than 0, okay, then you will be approaching along something like this. If y is greater than 0, okay, so if y is greater than 0, then x dot is positive. Okay. So if you are in this region, you will get a graph that shows x dot increasing, and then it will asymptotically go to x dot equal to 0. So this is what it will look like. If you are somewhere here, then what will happen is that you will go, let me just erase this point. Okay. So if you are somewhere in this region, okay, suppose you start with x and y both greater than 0. Okay. Now x dot equal to y, so y is greater than 0. Okay. So y will decrease and x will increase till it becomes parallel to this line, and then it will turn and go asymptotically towards this. So, that is what your trajectories will look like. When they cross the when they cross the x axis, they will always be perpendicular, because at this point y equal to 0. So, the rate of change of x is 0. So, it will cross in this manner. Okay. And similarly, you can extend for the other values also. Okay. So, so in this case, if y is negative, okay, then your points will essentially go in this manner and approach the origin, okay, and so on. Okay, so this is what your points look like. Now, suppose I start with a point at x equal to 1, y equal to 0. Okay. So, what will be the behavior of this point? So, since x is greater than 0, okay, x since y is equal to 0, x dot and you started at this point. Okay. So, x dot is going to be 0. So, it is going to be straight, okay, and if you see y dot is negative. So, y has to decrease. So, y will go down and it will follow this, and it will eventually come towards this point. Okay. So, this is what the picture of this oscillator is, of this damped harmonic oscillator is. Okay. Now, the next problem, okay, is a chemical reaction. Okay. So, in this chemical reaction, okay, I am writing the overall scheme. So, the overall reaction is A going to P, okay, some reactant going to a product, and there are various steps in this reaction. Okay. So, the first step is A reacting with I call it I1, okay, to give 2 I1. So, I1 might just be an excited state of A, or you know, it might just be some modified form of A. Then you have I1 plus I2, okay, I1 and I2 are 2 intermediates, okay, that gives 2 I2, okay, and then I2 going to P, and these are the rate constants. So, I have asked you to write the ODEs for I1 dot and I2 dot for fixed A equal to A0 equal to 1, and then you determine the phase picture, critical point, and nature of critical points for this problem. Okay. So, this is fairly straightforward. So, if I write I1 dot, okay, using your typical kinetics. So, I1 here, so I1 dot, okay, you can write it as K1 times A is the concentration of A, times I1, and you have minus K2 times I1 I2, and similarly I2 dot is equal to K2 I1 I2 minus K3 I2. Okay. And if A is equal to A0 equal to 1, then this looks like K1 I1 minus K2 I1 I2, and this looks like K2 I1 I2 minus K3 I2. So, this is the first thing that you have to write the ODEs for I1 dot and I2 dot at fixed A equal to A0 equal to 1. Okay. Then you have to determine the phase picture, critical points, and nature of critical points for K1 equal to 1, K2 equal to 0.5 and K3 equal to 0.1. So, let us write the equation. So, if I can write the equations as I1 dot is equal to K1, that is I1 minus 0.5 I1 I2, and I can write I2 dot is equal to minus 0.5 I1 I2 minus 0.1 I3. Okay. So, what are the critical points of this equation? So, this is a nonlinear equation, nonlinear system. Okay, so let us determine the critical points. So what are the critical points? So I1 is equal to 0.5 I1 I2. Okay. So and I2 this should be I2. And I2 is equal to 5 times I1 I2. Okay. So the critical points are 0 0, which is the uninteresting one, and what is the other critical point? Not interesting critical point. Okay. The other critical point is suppose so you get I2 equal to 2 and I1 equal to 0.2. Okay. So this critical point is 0.2 comma 2. Okay. So now let us linearize about so suppose you linearize system about this point. Okay, what will happen? Okay, so what you will get is I1. So you say I1 equal to 0.2 plus x, I2 is equal to 2 plus y. Okay. Then I can write this equation as I1 dot, it will be x dot is equal to I1, that is 0.2 plus x minus 0.5 0.2 plus x into I2 is 2 plus y. Okay. And what you will get is you have the 0.2 will cancel because of the first term. So, and the x, so you have 0.5 into x into 2. So, again that will cancel the x. Okay. So, so you will just have a term that involves y. So, you will have minus 0.5 y plus the xy term plus the xy term, which is nonlinear, plus nonlinear term, and y dot is equal to you. So if you write for y dot, what you will get is sorry, not 0.5 y, for 0.5 into 0.2 into y. So, that is 0.1 y. And if you look at y dot will have so y dot is 0.5 times 0.2 plus x 2 plus y minus 0.1 into 2 plus y. Okay. And in this case again you will find that the factor of 0.5 into 0.2 is 0.1, 0.1 into 2 is 0.2. So, that will cancel the 0.2, and then you have 0.5 into 0.2 into y, that is 0.1 y, which will cancel that. So, what you will be left with is 0.5 into x into 2, that is x. Okay. So, just 0.5 into x into 2, that is x, and plus nonlinear term. Okay. So, our linearized system looks like this, looks as x dot y dot is equal to 0 minus 0.1 1 0. Okay. So this is what our linearized system looks like. Now, eigenvalues, clearly the eigenvalues are purely imaginary. Lambda is equal to plus minus square root of 0.1, okay, I. So, purely imaginary. And if it is purely imaginary, okay, we know that it can be either a center or a spiral point. Okay. So this point is either a center or a spiral point, and that whether it is a center or a spiral point, this is for the nonlinear equation. So, Cp for nonlinear ODE, okay, this can be either a center or a spiral point. It is very important that this is for the nonlinear ODE. For the linear ODE, clearly this is this will be a center, okay, but for the nonlinear ODE it can also be a spiral point. Okay. So this is the what does the phase picture look like? Okay. So let us just try to draw some characteristics of the phase plane. So, I1, I2, okay, the 0 0 is a not so interesting point, okay, but the other point is given by I1 that is 0.2 and 2. So, 0.2 and 2. So, if it is a stable point, then the trajectories will look like if it is a the trajectories will look like this, around this. Okay. Or if it is a or if it is an unstable point, if it is a spiral point, then your trajectories will go spiraling towards this. Okay. So, you can we will just show what happens if it looks like a center. So, if it looks like a center, okay, then we go back to our nonlinear equations. So what we had was yeah. So, these are our nonlinear system of equations. So, I1 dot, okay, is I1 minus 0.5 I1 I2. And okay, if you go around the critical point, so if you look at the linear system, okay, then you have x dot equal to minus 0.1 y. So if in this case y is greater than 0, so the rate of change of x is negative, okay, around this point. So if x is, so you have for y in this region, so you have trajectories like this. Okay. You could also have it could also be a spiral. Okay. So, for some other values of the nonlinear equation, okay, it's slightly more difficult to analyze, but you could also have a spiral point, okay, which where the trajectories go spiraling towards this point. Could also have something like this. Okay. It really you have to do a bit more analysis of this nonlinear equation in order to get this. Okay. So, I will conclude this module for now. Okay. So this is the end of module 7. Okay. And in this I have tried to show you certain ways to analyze nonlinear differential equation. These are purely qualitative ways, okay, that give you some sort of picture of the nonlinear differential equation. Okay. And these are very interesting techniques, okay, and often you can get very good idea about nonlinear equations by analyzing the critical points. Okay. Thank you.